As massive globalization perpetuates, the deterioration of our air due to greenhouse gases has become a pressing concern to us. Air pollution has long been directly tied to congestion levels in cities, and it is no surprise today that cities with high congestion levels have also high pollution levels. At the Paris Climate Conference in December 2015, 195 countries adopted a universal climate deal which sets out to limit global warming to well below 2 degrees. The agreement is due to enter into force in 2020 and will force authorities around the globe to rethink their national climate policies. As nations undergo heavy urbanization, not only do governments have to think about their carbon footprint, but also the efficiency of their road networks. Dynamically optimizing both traffic and air quality across the country are tough and conflicting objectives, but can be tackled with the power of computing. Traffair aims to mitigate traffic congestion while meeting air quality standards by providing a smarter traffic management system based on air pollution levels across large cities. The Traffair system is based on a research project called iTrack from the De Montfort University, which gathers space data about greenhouse gases, meteorological information, and traffic levels to develop a statistical model that creates a navigation algorithm. We wanted to use data acquired on the ground to build a model that could predict the level of traffic at various locations based on their levels of nitrogen dioxide. When preparing for the project, we first investigated where to find the data to build our statistical model. We used the London Air API and the Here Maps Traffic API to gather data about nitrogen dioxide and traffic levels at various locations in London. Then, our hardware investigation concluded that the Raspberry Pi was the most suitable controller for nitrogen dioxide sensors. We kept the investigation of data analysis tools until a later stage, when we had gathered enough data. Traffair is powered by Watson's Predictive Analysis API, which offers real-time traffic level prediction based on statistical models built in SPSS. We concluded our design and preparation phase by establishing a strict timeline that would guide our development cycles and our meetings. This is Traffair's architecture. It uses public data to build a computational intelligence module, which provides statistical models used to predict traffic. When real-time data arrives from the sensors deployed in the wild, the traffic prediction module queries the statistical model to get traffic predictions. Once all the location's traffic levels are estimated, the routing algorithm provides the optimized path for the traffic lights to abide to. This real-time data is then available on a user-friendly monitoring dashboard and through a public API that allows anyone to integrate with the Traffair system. Traffair is built with Raspberry Pi and nitrogen dioxide sensors connected to the cloud computing platform, which acts as the computer intelligence, traffic prediction, and routing modules. It is powered by IBM Bluemix and Node-RED, where the data gathering, the statistical, and the prediction models are hosted. The statistical model is built with IBM SPSS Modeler, based on the data gathered over 2 weeks period from the London Air API and the Here Traffic API. This SPSS model is then uploaded to Watson's Predictive Analysis service and used in Node-RED as an API to predict the traffic levels. All of the predictive information is beautifully outputted in a user-friendly monitoring dashboard and also available as a public API. We then used Excel and MATLAB to perform offline analytics on the comparison between our prediction and the actual measured traffic levels. Preliminary results of our system have showed us that we are onto something, but we still have some margins for improvements, especially concerning the statistical model that we built. Comparing predicted traffic levels with measured ones showed that our system is able to pick up on trends such as rush hour or quiet hours, but is not yet fully capable of providing accurate predictions with high confidence levels. This is mostly due to the fact that our model estimates time of the day to be a more important predictor than nitrogen dioxide, due to the discrepancies in the classifier that we built. A quick MATLAB analysis illustrates that our classifier needs some further work in order to pin down a much more constant and lower error rate. We hope that you are as excited as we are about the potential of Traffair. We hope to bring this solution soon to many cities to help improve the traffic networks and the air quality around the globe. What we have here is our test bed for the system. We've replaced the KC5 location with one of our sensors that outputs nitrogen dioxide, and it simulates the KC5 locations. And so it sends the data in real time to Node-RED over here, and then it outputs in real time on our dashboard every 5 seconds at the moment. And as you can see, this is the location that we're simulating, which has a fairly low nitrogen dioxide level because we're not in traffic at the moment. So now we have the scenario where we've replaced the London Air API KC5 location with one of our own sensors right here. And our sensor is in the wild, currently gathering some data. And we see the redirection from KC4 to KC3 with our sensor at location KC5. And so we will now strike a match to simulate high gas readings. All right. And so what we should see immediately is an update in the location here, where we have a higher reading and a different routing.
My name is Said Hassan, and for the IoT project I was in charge of hardware implementation, and we had to collect pollution data from an NO2 sensor, and the NO2 sensor was then connected to an Arduino, and the Arduino then pushed the data to a Raspberry Pi, and the Raspberry Pi acted as a gateway to IBM Bluemix, and I was in charge of writing the code for pushing the data from the Raspberry Pi to Bluemix and collecting the data from the sensors through the Arduino IDE.
And I built the cloud part of this application using IBM Bluemix and Node-RED. And this cloud part is divided into two parts. The first one being the data gathering model, which uses a few APIs that you saw in this video, and also the predictive model, which is based on the sensor readings we had from the hardware, along with the Watson predictive analysis system.
Hi, my name is Duman Makhambetov, and my responsibility in this project was about connecting Raspberry Pi to the IBM Bluemix platform. And basically, I was a team assistant of Sasha. Our main responsibility was about finding out London air quality API and here traffic APIs, and trying to push the data to the Node-RED application.
My name is Laurie, and in this project I'm mainly focused on the data analytics. For the data analytics model, I chose the neural networks as a basic algorithm. And this algorithm runs on MATLAB. And in addition, I also do some regression analytics to find the relationships between the inputs and outputs.